Thank you very much. Dear distinguished guests, probably from the way I wear my tie, it's quite clear that I'm not really good with all this formal stuff. So, hello friends. I'm really happy that all you made it here. Some without complications, some with some complications, but we eventually made it here. And I'm very happy that you came and that you're here to listen to what I say. And I would like also to thank the Scientific Council for choosing this topic, because there were 3 topics to choose from, and I was kind of hoping that they will choose this one. So I'm thanks to them also. Let me begin in the very beginning. And also my thesis starts with a sentence starting from the work of Newton in the 17th century. The physicists have been on a steady march towards unification. So this is a very simplified diagram of history of physics. A lot of interesting things are happening here. Each and every arrow is worth a lecture of its own, but the idea here is quite clear. Apart from the fact that always make fun of chemists if you can, there is a steady march of things getting together and of different ideas being merged into one consistent idea. And this way, from Newton in the 17th century, we ended up with 2 theories here on the right. We have quantum theory of elementary particles, which we call standard model, which is theory of matter, of particles and its interactions. These are the elementary particles of standard model, or some of them together with all the antiparticles and different color and other charges of the particles. And these are the elementary particles, and they form the more complicated things that we know as protons, and then atoms and everything around us. So this theory governs the matter that our world is made of, and it is a quantum theory. On the other hand, we have general relativity, a classical theory that describes the gravitational interaction as a curvature of space-time. But it also describes a lot of other interesting features, including the history and dynamics of the universe as a whole. Now, this is a very nice, pedagogical, but extremely wrong depiction of the curvature of space-time and of the idea of general relativity. This is much better, but I understand much less understandable depiction of what's going on there. These are the Einstein equations of general relativity. And what for you to take from here is that in this object here, matter is encoded and the way that things are arranged in the universe. And in these objects, the curvature of the space-time is encoded. And these equations tell us that these 2 things are interlocked, and that matter affects the space, and then space moves in this curved space-time as if it was moving under the force of gravity. But as I said, there is a steady march of unification as you go from past to present, and now one would like to know whether there is the last obvious step to be made. And people have been trying to formulate unified theory and find the quantum theory of gravity. And usually in physics lectures or in this kind of outreach lectures, people go, and this is the way you do it. And we don't know. We don't have quantum theory of gravity, and it's not for lack of trying. A lot of people have been trying to figure something out, and we don't have the final theory. We don't have the theory that would incorporate both the matter and the quantum, both matter and the gravity and the space-time. Now the problem is that when you try to do so, you start mixing apples with oranges. And when I was translating my slides from Slovak to English, I also had to translate this image, because in Slovak it's apples and pears, and in English is apples and oranges. So because when you have Einstein equations, here from mathematical point of view, matter is described by quantum theory, by algebraic theory of operators and Hilbert spaces. General relativity as a geometrical theory of curvature, smooth manifolds, and things like that. And these two things don't really talk to each other, as is usually said. But this is not completely true, because we have quantum theory of electromagnetism, which has similar issues in Maxwell equations. So there is a way how to write quantum theory of electromagnetic interactions, and there you can mix apples and oranges together. But it turns out that general relativity is more complicated theory. In technical terms, it's not renormalizable, and you cannot play the game you played with electromagnetism here. And when you try to naively quantize the left part of these equations, you end up with something that doesn't make sense. So it turns out that general relativity is proper oranges that cannot be mixed with the apples. And on that note, I'm going, as I said, we're friends. I'm not trying to sell you anything apart from my work. We don't necessarily need the last step in the diagram. Nobody guaranteed that there was going to be a final theory, one unified theory of everything. Perhaps the world is made in a way that we have two fundamental theories describing those two interactions separately. However, we definitely need quantum theory of gravity. Gravity has to be quantized because matter is quantum, and since matter interacts with space-time through Einstein equations, also the space-time needs to be quantized. If at the end of the day we are able to incorporate these two theories together, that's an open question, and maybe it's not possible. However, I would suggest that the diagram is a strong indication that, it would be pity if it wasn't that way. But if you are to remember one thing from what I'm going to say today, I suggest it is this slide, that any attempt to unify quantum mechanics with gravitation predicts some kind of structure of space, that eventually space is not going to be a smooth, continuous object, but is going to be coarse-grained and is going to be composed of something. Now, what does it mean to be composed of something? Well, usual things, like a person or an image, or at the end of the day, the matter, is composed of some objects that are put together in a well-defined way, and then they act as one object, for example, like I do right now. However, we also know that atoms also have some kind of structure. There are electrons, protons, and neutrons, and protons are composed, again, of something deeper. But this composition is very different. It's governed by quantum mechanics. And quantum mechanics, with its uncertainty principle, says that this composition is very different from the way I'm composed of my limbs. That this image is very misleading. There's nothing as a path of the electron. Electron is not a ball, but is a point particle, but we don't really know where it is. And this is a much better image of an atom, that it's some kind of nucleus and then some cloud of electronness around where the electron is or is not or may be. So now when we're talking about the true fundamental components of our world, being composed of something is a little different than being, that pieces stitched together. Now, what scales are we talking about? Perhaps you remember from your high school science classes that atoms are this large, and you might remember that this is very small. That, for example, when you take atom and you make it as large as the apple that I mentioned, the apple in this scaling would become as large as a planet. I don't know if this tells something to you. I probably said this story like 100 times, and I still don't feel I really feel the smallness of the atoms. This just tells me that, again, it's so very, very small. But atoms are small compared to us. But for example, if you look at nucleus, which is 5 orders of magnitude smaller than the atom, then atom is huge. Because if we enlarge the atom to be the size of our planet, then the nucleus is size of a typical building. So now, are atoms large or are atoms small? Well, it depends on who is asking the question. What are you comparing against? And SI units are, they are made by engineers, and they are good for us for describing processes that we usually encounter. But perhaps the fundamental laws of nature have different suitable units. And there are natural units of nature. In English, this sounds much better than in Slovak, actually. So I like this slide also much better in English. And we are seeking theory that would incorporate both quantum mechanics, both theory of relativity, and both gravity. These all come with its own fundamental constant, and you could say that these are the fundamental constants of nature. And then Planck asked a question more than 100 years ago: how do we combine these three to create quantities of length, time, and mass? And you can do it in just one way, and these are the numbers that you end up with. So you end up with ridiculously small length, ridiculously small time, and kind of smallish mass, but it's not as small as the other ones. So what's happening here? And the point is, this is very small when compared to masses of elementary particles, for example. So that it's very large. Sorry, it's very different from masses of elementary particles. So elementary particles are very small compared to this. Or if you translate this to Planck density, that this is proper humongous number, and we can go further. So at these scales, we expect all the three theories to be important at the same time. Yeah, at the speeds and length scales and time scales that we ordinary people work, usually quantum mechanics and special theory of relativity are not too important, and only the gravity is something that we need to take into account. But if we are to describe a process of this time scale, this length scale, and this density scale, then we need to have proper quantum theory of gravity. Well, this would be a good point to take questions, if there are any.
Proceed, and the question will follow after.
And also, that was a good point for me to take a drink. So, how does one come with the notion or with the necessity of a quantized spacetime, of the quantum structure of things happening at small length scale? So, from quantum mechanics, we know that if you make particles smaller and smaller and smaller, the particles gain more and more energy. This is idea due to de Broglie, and the smaller you make a particle, the larger energy it carries. Now, from general relativity, we know that if you pack too much energy into a small enough region, you create a black hole and a horizon and all those things. So that means that if you start creating more and more energetic a particle, then at certain point you create a black hole. Now, why is this a problem? Well, if you're trying to see what's in here, what you do is you take a particle, you smash it against your target, the particle bounces off, and it carries some information about the object that has been hidden there. And what's been hidden here is our old logo of Comenius University. And if you want to see it more finely, then what you need to do is you need to take a smaller particle. It's like if you're throwing a basketball against the fence, nothing happens. But if you take a ping pong ball and throw it against the wire fence, then the ping pong ball is going to do funny things because it's going to see the holes in the fence. So similarly, if you take a smaller particle, you can see a nicer image of our old logo. And the reason I have used old logo and not the new one is that if I made this more pixelated, you wouldn't really see a difference. So, but when you try to make particles smaller and smaller and smaller, at a certain point, you're going to create a black hole. And anything that happens under the horizon of the black hole is hidden from you. You cannot really see it anymore. And if you do back of the envelope calculation, you will find out that this happens exactly at the Planck scale. So this means that if we are interested in features of images or anything of scales Planck length and smaller, we're fundamentally not able to gain this information, because it's going to be hidden under the horizon of the black hole that we accidentally created while trying to figure out these things. So processes under the Planck scale are hidden from us fundamentally. But this doesn't necessarily mean that they cannot exist. They just can live there separated from whatever we huge beings of order 1 meter are trying to see. But if you do a more refined analysis, you use the feature of quantum mechanics that there are quantum fluctuations, that vacuum is not truly an empty space, but is a bubbly soup of particles appearing and disappearing. Then, and combine this with the general relativity creation of black holes, then you find out that large enough fluctuations in the vacuum are going to create black holes. That there is a possibility of black holes being created from the quantum fluctuations of matter fields. And there is a complicated calculation that goes with this, but the result is that this should happen, and this should happen at the scale that the vacuum should be unstable against these fluctuations. So the prediction is that if you combine quantum theory and general relativity, the vacuum will fastly disintegrate into slew of tiny and larger black holes. Now we're going to do an experiment. I guess you didn't expect an experiment in a theoretical physics lecture. We're going to observe whether or not vacuum of our space is going to disintegrate into black holes in a very small fraction of time. It didn't. Well, this is a theoretical physics lecture, so better experiments are not to be expected. So we don't observe these instabilities. And the most straightforward solution to solve this is to say that nothing that small can, in principle, be created. That there is some structure in the space that forbids these small fluctuations that are too energetic and would lead to instabilities. So we postulate some kind of structure at the scales of Planck length, and I just now realized I have the image here right in front of me, so I don't need to look here. And this structure would fix this instability. The vacuum would become stable in such a space, and everything would be fine. And now, what kind of structures can we come up with that have this quantum structure of space that don't allow us to pack arbitrarily large energies into arbitrarily small regions? Well, we've seen one example when we played as kids with graph paper, and we drew images in here where you tried and created image from pixels like this. But this is a space that has quantum structure. If you say that nothing within this square is separated from one another, and this square as a whole is one entity that the space is composed of, then this is space of quantum structure. However, this space doesn't have the original symmetry of the blank paper, because there are different images that you can draw on this paper and on blank paper. Because if I move this by half of the lattice side, then I get a different paper. I get ability to draw different images. So what we say is that the symmetry of this paper, of this space, is smaller than the symmetry of the original blank paper. And this is something that we would not like to happen. That in physics, we're used to the fact that symmetries play a crucial role, and we would like we formulate our theories based on the symmetries that we have, and we would like to have space that has as much symmetry of the original space as possible. So different way how to realize this is something that I, for the purpose of this talk, when I give it, call bubble space, because this is this is an image that a lot of people are familiar with. And the point is that in this space, we again have some kind of quantum structure that if you say that all these bubbles are entities on its own, then there are larger bubbles, smaller bubbles, but at the end of the day, you can locate the smallest bubble and nothing can be smaller than this. But, the bubbles can move around. The bubbles can be squeezed and stretched. So in this sense, the quantization is not that rigid. It's more symmetric. But still, there would be the smallest size of a bubble. And if you tried to squeeze this bubble into smaller region in this direction, then the bubble would spread out in this other direction, and you would still retain a characteristical length scale and effectively the smallest possible volume. You might have seen something like this in the entrance into this building, and this is similar in idea, but usually if I showed this picture to people that don't often come to this building, they wouldn't understand why it is important. But again, we have some irregular pattern of cells where we can locate the smallest possible cell, and we usually don't allow dynamics in floors. If your floor is dynamical, it's not really a proper floor. But in principle, you can imagine that these things could be stretched and squeezed around. Bubble space is something that is a name that I have invented. And it's usually this is referred to as non-commutative or fuzzy spaces because the idea to construct these spaces comes from quantum mechanics. In quantum mechanics, and I am trying to persuade you that I know some physics, and physics is equations. So I managed to squeeze one equation into my habilitation lecture. Or there were Einstein equations, but there were more of an image than an equation, because here X and P are position and momentum operators, and in quantum mechanics, the essence of uncertainty principle is here, that these operators do not commute, and therefore you cannot measure position and momentum of a particle arbitrarily precisely. If you know really well where the particle is, then your uncertainty in its momentum is really large. And you can play the same game with position operators. You can postulate some commutation relation among the position operators, and then the same thing is going to happen in your coordinate space, that you cannot locate anything arbitrarily precisely in X and Y directions simultaneously. And there's exactly this idea that if I know X coordinate really precisely, then my uncertainty in Y coordinate is really, really large. And something like this happens there, but the opposite way. that this image should work like that, that if you look at certain place, then the snakes start to swirl around at the places where you're not looking at, and then when you try to follow the swirling places, that they run away from you. And in non-commutative spaces, the opposite things happen, that if you look somewhere, it swirls, but somewhere else, it's nice and steady. And if you look at steady part of the image, it starts to swirl. And the closer you look, the more it swirls around. So this way, we are able to construct a space that is symmetric, yet has some kind of quantum structure. And then you can go absolutely bananas, and you can say that space itself doesn't exist. That things like position, speed, etc., that we usually relate to spatial positions, is created by interaction of the particles with some other hidden degrees of freedom, and the idea of position only emerges from the interaction with these degrees of freedom. We call things like this emergent spacetimes, and they can appear in theories like matrix formalizations of string theory. And the interesting thing is that there is a very natural way how to formulate a model motivated by string theory that doesn't include space-time as continuous manifold where particles and other matter moves, but the dynamics of that model creates this idea of space, and the spaces that you obtain there are exactly the non-commutative spaces that I have been talking about. So emergent spacetimes in some way are also related to the non-commutative spaces that I mentioned before. So, and now the obvious question for last 3 minutes is, can we see the quantum structure of spacetime? We cannot. So my job security is quite fine, isn't it? But we can see it indirectly. For example, this is the cosmic microwave background image where these dots are related to the quantum fluctuations in the early universe. And as I have established, quantum fluctuations are related to the quantum structure of spacetime. Now, we cannot see that well yet. But as you can see, over each 10 years, the resolution of our understanding of CMB gets better and better and better. And probably we can hope for an image here that would be able to capture some features of the quantum spacetime. Then there are some things that Samuel will talk later in the afternoon about, that in quantum spacetimes, light doesn't travel. Not all wavelengths of light travel by the same speed. Very energetic photons travel a little differently because they start to see the fine structure in the spacetime, and perhaps we can see consequences of this in high energy gamma ray bursts. Then on the opposite end, tiny black holes live at the order of Planck length. So physics of miniature black holes is related to physics at the quantum structure scale, and there are some consequences of that again, perhaps you will see, you will hear about later today. And then we can have particles like charmonium that are small enough to actually be sensitive to the quantum structure. In charmonium, the quarks are effectively at the length of roughly 10 to the negative 16, so that's even order less than the size of nucleus, and it's still quite far away from Planck length, but perhaps when we find different particles or are able to describe physics of this particle better, we can start seeing consequences of the quantum structure that this particle lives in, and is more sensitive to, because it's much smaller than anything else that we encounter. And the other thing is that perhaps, it's not like we have 16 different candidates for quantum theory of gravity, and we need to pick one. We don't have any consistent quantum theory of gravity. And perhaps if at the end of the day somebody really, really smart comes up with a consistent quantum theory of gravity, perhaps they will be able to show that this is the only possible way this can be done. And then perhaps we will be able to say something about the quantum structure, and we will be able to see the quantum structure from comfort of our offices, and we will not have to go out to the wild. So with that, I would like to repeat the one thing that I hope all of you will remember from my presentation. And as I said, we don't really know yet what the quantum structure is, but it is an important step towards construction of the eventual quantum theory of gravity and perhaps the unified theory of everything. Thanks for your attention.